This is our second module in the lecture series for the short course on spatially variant lattices. In this module, we will learn the theory and how to spatially vary just planar grating. So we're not talking about lattices yet. That will be module 3. Before we talk about generating spatially variant gratings, there's two concepts that we need to introduce and that you really need to get a good solid understanding of. One is the grating vector and the second is the grating phase. Once we have a grasp of those two things, and they're very tightly related, then we can go in and talk about how to spatially vary planar gratings, which of course are described by the grating vector. Onto the grating vector, and we write this as a capital K. So here is a picture of the grating vector in 2 dimensions. The image that we see at the upper left, we see these thick black lines. The thick black lines is our planar grating. This thick blue arrow, this is the grating vector. Notice it is oriented perpendicular to the black lines. So if we think of these black lines as a wave, for example, the wave would be moving toward the upper right or maybe the lower left. And this grating vector is pointing in the direction that wave would move. So the grating vector is carrying 2 pieces of information, and we just talked about one of them. The orientation of the grating vector is perpendicular to the black lines, the planes of the grating. The second piece of information it carries is through its magnitude. The magnitude of the vector is 2 pi divided by the period of the grating. So if we come over here and we look at the spacing between 2 planes in the grating, we'll call that capital lambda. The magnitude of k is 2 pi divided by lambda. And that may seem kind of a crazy way to define the magnitude, but the reason that that is very useful is that if we want to calculate or generate this planar grating, it's as simple as calculating cosine of k dot r, where r is the position vector, x, y, z. So by defining it 2 pi over lambda and putting it in the direction perpendicular to the planes of the grating, it makes it very easy to calculate the grating itself. We just calculate it as cosine of k dot r. The grating vector exists just as well in 3 dimensions and is defined exactly the same way. Here I'm trying to show a 3-dimensional grating, or at least just a portion of it, as best as I can with these little fuzzed out regions. But it also has a period in whatever direction this may be, and our grating vector is still perpendicular to the planes of the grating, and its magnitude is still 2 pi divided by the period of the grating. And this still lets us calculate, even in 3 dimensions, it lets us calculate this grating using cosine of k dot r, where r is still the position vector. So we can use the grating vector in 1, 2, 3 dimensions, probably more dimensions, but I don't even know what that would mean. So I live in a 3-dimensional world, so my vectors are 3-dimensional. Some terminology here. What we've been showing is what we would call analog gratings. You'll notice if we look at the picture of the grating, we have certainly black, we have certainly white, but we also have these shades of gray in between. And in fact, if we were to run our fingers along this, we would feel a smooth cosine profile. That makes sense. We calculated it with a cosine k dot r. So we'll designate what we're calling this analog grating with an A subscript. And the analog grating is limited either between -1 and 1, or sometimes we'll do between 0 and 1. And we can calculate it either with a cosine k dot r or equivalently as the real part of a complex exponential of k dot r. And if we ever wanted to convert this analog grating into something real that might have permittivity values, we would take our cosine k dot r, multiply it by the permittivity contrast, in other words, the magnitudes of the swings or the modulation in the permittivity, and we might add to it some average value of permittivity. So Even still, we're calculating this from cosine k dot r. We're just scaling it in a way that would give us real permittivities, and we'd come away with our permittivity function. Instead, and it's more common, particularly for us, to talk about what we'll call the binary grating. And with the binary grating, instead of having this smooth black, white, and grays in betweens, we only have black or white. And we can calculate this binary grating from the analog grating just through a simple threshold operation. So we can say, or calculate cosine k dot r, and anywhere that it's greater than 0, we'll set this to 1s. Anywhere it's less than or equal to 0, we'll set it to 0. So we just are left with 0s and 1s, and that's what we call our binary grating. Now, a lot of times that's preferred because when we're manufacturing something, actually building a device, to functionally grade the permittivity is difficult. Not impossible, but difficult. More often, we just want material or not material, plastic, air. And so we don't really have these in-between permittivities. Further, by controlling the value of this threshold, we can set the fill fraction. So on the right-hand side, we set our threshold to a value of 0.8, and we have fat black lines. I'm not showing it here, but had we use a value of, let's say, negative 0.8, it would look inverted. We'd have skinny black lines and thick white lines. So by controlling that threshold, we control the fill fraction. On to our next concept, which can be confusing, and this is called grating phase. I think this is confusing because normally we associate phase with waves, and now we have a grating. It's not moving anywhere. And so I'll do my best to make this as clear as possible, but it's definitely borrowed from the concept of waves. So let's look at the form of a plane wave. We could write it this way. It has some amplitude and polarization, and multiplying that is a cosine term. There's a k dot r minus an omega t. Now here it's a lowercase k. That's called the wave vector. And the wave vector is defined very similar to our grating vector. The wave vector is perpendicular to the planes of equal phase of a wave, and it's in a direction perpendicular, and the magnitude is 2 pi divided by the period of the wave. So the grating vector was perpendicular to the planes of the grating, 2 pi divided by the period of the grating. Wave vector, perpendicular to planes of equal phase, magnitude 2 pi divided by the wavelength. So they're defined similarly. So the lowercase k and capital K will make an analogy, and we will connect those. And so we'll say our wave to grating analogy, little k has the role of big K. Now we can look at the entire argument of the cosine and say that that is the phase of the wave, and we'll call that little phi. So little phi is just k dot r minus omega t. And so this little phi, the phase of a wave, which if we're familiar with waves makes some sense to us, then it makes a little more sense that we could define phase of a grating. Now the phase function of a wave, it's a moving phenomenon, whereas our grating's still. So the capital phi doesn't move. It's a static concept. And also in our analogy, instead of having an electric field in the wave, we might have a permittivity. Maybe it's a permeability, maybe it's a conductivity or something else, but some kind of function that we are spatially varying. So if we look at these functions, we'll call this our k function. It's a bunch of arrows pointing in some particular direction. And the direction it's pointing is the way the wave is moving or how our planar grating will be oriented. We could also think of our wave in terms of this phase. So here we're looking at a phase function, and we can see, yeah, okay, as the wave is propagating from lower left to upper right, it is accumulating phase, so that phase function increases in the direction that the k's are pointed. And then if we calculate cosine of phi, we can see our wave. I've thresholded it here, so that's not a binary lattice, or it's not an analog lattice, it's a binary lattice. But that would be what our wave would look like. So this concept of grating phase, we're borrowing it from waves, but when we calculate this function, capital phi, it doesn't move, it's stationary. And it's always increasing in the direction that the grating vector is pointing. Let's look a little bit more of grating phase and try to give it a definition. Let's make a first guess at a definition. So we already know that we can construct our analog grating with a cosine k dot r. What we'd like to do is calculate it with a cosine phi, just like what we did for a wave. That would suggest that our grating phase is defined as k dot r. And what we'll see is this is not the most rigorous definition, but let's go with this. So if phi is k dot r, what is k dot r? It's just the x component of k times x plus the y component of k times y. So that's just 2 dimensions. That's the dot product. So if we created a 2-dimensional map of the x component of x, and we created a 2-dimensional array describing the position of each point in x, we'll call that capital X, we could do a point-by-point multiplication of these arrays. And likewise, we'll have a map of ky everywhere, a map of the y positions everywhere, do a point-by-point multiplication, and add all of these up, and we get our grating phase. Then if we calculate cosine phi, sure enough, we get an analog grating. So this all seems well and good, but what we'll find out when we try to spatially vary something and our grating vector becomes a function of position, this breaks down and requires us to handle this differently. So let's do the simplest of spatial variants, and let's think about a chirped grating. So we have a grating here in the upper right that starts with a short period and goes to long period. That means we'll start off, we could describe the period this way, where we have some constant lambda naught times z. This is describing the period, and since it's multiplying z, it gets bigger with position. And so when we spatially vary the period in this manner, we call that a chirped grating. Well, let's see what its grating vector function will look like. We can write this as a scalar because we're just talking about spatial variance in one direction, so it's only dependent on z. It's defined as 2 pi over the period, and the period is this lambda naught z. So our k as a function of z is 2 pi divided by this constant lambda naught, and also being divided by z. Well, let's see what happens when we try to construct this chirped grating with cosine k dot r. So in one dimension, our cosine k dot r becomes cosine k times z. So we'll take this whole argument and write it over here, but now our k function is 2 pi over lambda naught z times z. Well, these two z's cancel, and we end up just with 2 pi over lambda naught. This becomes a constant and definitely does not form a chirped grating. So something is wrong here, and what's wrong is we don't have the most rigorous definition of how our grating vector is related to the grating phase. This path made intuitive sense, but clearly something's wrong here. So we need to do something different. We just showed that phi, the grating phase, can't be k dot r. That only works for the special case when k is a constant. As soon as it's a function of position, it no longer works. We know we can calculate our analog grating with cosine phi, so how is phi related to k? And here it is, and this really is the key equation when we're spatially varying planar gratings. It's the gradient of phi that equals k. Not phi equals k dot r, but k is the gradient of phi. And what we'll do is we will build maps or pictures of what k looks like, because that's pretty easy, and we will solve this differential equation for the grating phase, and then once we do that, we can easily calculate the analog grating. But solving this is not necessarily easy or straightforward. Okay, so we think we've fixed our problem. Let's give it a try. So right away, del phi equals k. Let's work through the math. We're in one dimension here, so the gradient operation in one dimension is simply the ordinary derivative with respect to z, and our k as a function of position here is just 2 pi over lambda naught z. So we solve this differential equation by phi. It turns out that's pretty easy. We do that by integration, and we end up with this equation. This is an equation for our grating phase using our more rigorous definition. Now let's see what we get when we construct a grating. Our analog grating is cosine of the grating phase. We take our function, our expression for the grating phase, put it in down here, and now we have z here. So things are changing here, and it turns out we get our spatially variant grating or our chirped grating. So this definition appears to work, and as soon as the grating vector becomes a function of position, we have to adopt this more rigorous definition of the grating phase. We are now armed with all the concepts we'll need to discuss the algorithm for generating spatially variant planar gratings. So let's dive right into it. Here's the procedure. It's a 4-step process. The first step is we will build our spatially variant, if you will, or our grating vector as a function of position. And in our MATLAB codes, what you'll see is we'll be creating 2-dimensional arrays and then later 3-dimensional arrays that describe the x, y, and z components at each point in our grid that we set up, our array. But in closed form, our grating vector as a function of position, we'll call this our k function, is 2 pi divided by the period as a function of position, and it's a vector, so it has an x and a y component and a z component for 3 dimensions, but we'll stick for 2 dimensions right now. And so the x component has a weight of cosine theta, where now we have theta, the orientation of our grating as a function of position, and then the y component, sine of theta. So we will build maps or pictures of our period and the angle of our planar grating. And from that, we can calculate our k function. A k function really is the ultimate goal. From there, when we have the k function, we will solve this differential equation for the grating phase. Once we have the grating phase, then we calculate the analog grating, just from cosine phi. Once we have the analog grating, we can now calculate the binary grating using a threshold technique. And essentially, if the value of our analog grating is less than or equal to some threshold, we'll set our epsilon to epsilon 1. If it's greater than that threshold, we'll set it to an epsilon 2. And we really could define multiple thresholds and have multiple materials if we wanted to. We'll stick with 2 right now because binary lattices are definitely the most common for us anyway when we're manufacturing devices. But that's the step. So it's k function, grating phase, analog grating, binary grating. K phi analog binary, and that's how we remember it. And there's a block diagram of this on the bottom. And we'll always apply those 4 steps to generate spatially variant planar gratings. So here's some examples. I promised you we would generate pictures of the orientation of the grating in terms of degrees, or in this case we're using radians, the period of the grating, and then this threshold. We can change the threshold as a function of position to change the fill fraction as a function of position. So at the beginning of our codes, we'll be creating 2-dimensional arrays, later 3-dimensional arrays, and these are our input arguments. From this, we start doing our algorithm. We'll build the k function. We'll solve for the grating phase. Here's the grating phase that would come out of this. And notice we have a grating essentially moving left to right. And here would be our resulting binary grating. So here, really nothing's happening. We've chosen some orientation. The period and the threshold are constant, and so we get a vertical grating. Nothing real interesting happened there. So let's go ahead and do something. Let's put a little bloated circle in the middle of our theta function. What this means is, out here, we're still in the black. We want vertical lines here. However, inside this region, we'll want the lines oriented at 45 degrees. We still won't do anything with period or threshold. We'll leave those the same. So we just want to spatially vary the orientation of the grating. However, we want to do this, but still have the grating lines be smooth, continuous, and free of defects. So what does this look like? What comes out of this is our grating phase, and then our ultimate grating. And what we can see is that inside the circle region, it is oriented at 45 degrees, and outside is very near vertical. And that's what comes out of the algorithm. All right, let's do something else. Let's leave the theta function alone, and we'll spatially vary the period. We're chirping it from top to bottom in some manner. And we're still leaving the threshold alone. So what happens if we do this? What does our grating phase look like? And what does our grating look like after that? And here we go. And what we see is that we have a long period grating at the top and a short period grating at the bottom. And it chirps from top to bottom just how we prescribed over here. Orientation and the fill fraction are as constant as it can be. We notice the orientation is a little bit tilted here, and that's just due to the fact that we cannot make these lattices perfect, but the algorithm certainly has minimized the skew in those lines, if you will. And there's things we can do to improve that. Okay, let's leave the orientation alone. Let's leave the period alone. Let's just spatially vary the threshold. So what we should see is all vertical lines, but they should get skinnier and fatter inside and outside the black and white regions. So let's see what that looks like. And we see we have it. We have skinny lines out here and fat lines in the square region. So the next thing I'll show you is a very powerful property of this algorithm. Suppose we wanted to do all three at the same time. And we're talking about three different geometric attributes of our planar grating now. Its orientation, its period, and its fill fraction. And we want to spatially vary these all at the same time, all in different patterns, and yet we still want a grating that is smooth, continuous, and defect-free. And that's what we get. So we've spatially varied all of those at the same time and generated a very high quality lattice while doing that. So that's what this algorithm can do. So the first step in this, and we've connected it to some MATLAB code on the right, and of course we also have the computer sessions that writes very similar code. But at the beginning, we will build our input functions. I'm not showing the fill fraction function here, I'm only showing period and theta, but we'll define two-dimensional arrays to define period and orientation. So at the beginning of the MATLAB code, we're defining the period of the grating, and evidently we want to fill in two different values of permittivity. That would come at the end of the code. We wouldn't need that right now. And we're setting our threshold value to 0. That will end up giving us a grating with a 50% fill fraction, but we can control that. We want an overall grating that is 5 periods wide and then the same 5 periods tall. We're setting up a two-dimensional array that's 100 by 100 points to represent this 5 by 5 period grating that we want. Now we need to calculate our grid, and dx will be the size of each cell. There'll be 100 cells. How wide is each one? It's dx. How tall is each of these cells? That's dy. And we're calculating these as physical width divided by the number of points. So our physical width is 5 periods. We divide by 100 points, and we get the width of each cell. Then we create two arrays. So these pictures will be 100 by 100 points. Each of those 100 points has a position along the x-axis. And that's what XA is. It's our x-axis. And first we create an integer array that goes 1, 2, 3, 4, 5, all the way up to 100. And then if we multiply that by dx, we get an array telling us the position of each of those points. We do the same thing for YA, and then we do a mesh grid call. If you don't know the mesh grid command, that's very useful in MATLAB. I would jump to Google at this point and learn that command. It's very useful for us. At this point, we're in a position to calculate our two-dimensional arrays, PER for period and theta for theta. So period, we're just going to make A everywhere. So ones, nx, ny, creates a big two-dimensional array that's 100 by 100 of all ones. So if we multiply it by A, it'll be filled with A everywhere. Then theta, we have this weird arcing pattern, and that's easy to calculate. It's just the inverse tangent of yx. So that's the first step. We build our input functions, and from that, our spatial variance happens. Now that we have these period and theta functions, just in 2 lines of MATLAB code, we can calculate the x and y components of k. So this is calculating our k function. Remember how this is defined. Our x component of the grading vector function is 2 pi over the period times cosine of theta. So that's exactly what we have here. 2 pi divided by the period times cosine theta. The only sort of trick here is notice it's a dot divided by and a dot times. That's doing point-by-point division and point-by-point multiplication. If we don't have that, MATLAB will think it's manipulating matrices and start doing matrix multiplication, matrix division, which takes a heck of a lot longer and definitely leads to the wrong answer here. So in 2 lines of code, we went from our map of period, our map of orientation, and constructed our k function. Now, and this really is a difficult step, fortunately in this short course, we've made it pretty easy. But we need to solve this differential equation. We have k equals del phi. We can expand this into sort of a matrix form, and here we're using the finite difference method, although we could use finite element method or probably a variety of other numerical techniques. But one thing I wanted to point out is that we're trying to control 2 things, x and y, with only one unknown phi. So we're limited in our degrees of freedom here. Since we just have one phi and we're trying to control kx and ky, we can't do that exactly. It's a best fit. And so what we're doing here is solving it in the sense of least squares. The solution to this is not something we need to worry about in this short course. I provide a code called SVL solve. You give it kx and ky, the x and y components of your grading vector function. You also give it dx and dy, which is the width and height of the cell in your grid, and it provides this phi function for you. So it's very easy to use. Okay, at this point we have the grading phase, and it may look something like this, and if we generated a binary grading from it, it might look like that. But here I want to point something out. Notice how slow and smooth this grading phase is, whereas if we look at the actual grading, it varies very abruptly. And it turns out our grading really needs many, many, many more points on the grid until it looks smooth like this. If we have too few points, it will look staircased and ugly. Whereas if we used few points over on the grading phase grid, it still would pretty much look like this. So the whole thing that this lets us do is use fewer points for all of our data up to the grading phase. And then once we have that, we can then interpolate our grading phase up to a much higher resolution grid and then calculate the analog and binary gradings. And so the choke point in this algorithm is when we solve phi, because that's our big numerical step. So if we can do that on a grid with much fewer points, then it really improves the efficiency. So that's what we're going to do here. So in our codes, we'll actually have 2 different grids at work here. So as I mentioned, grading phase will be on a very coarse grid. And what do we define on this low resolution grid? Our period function, our theta function. Ultimately, we calculate our k function from these 2 things. That's still in the low resolution grid. And then we also calculate our grading phase, still on this low resolution function. At that point, we interpolate up to a phi 2 on our high resolution grid. Now in the code, since we don't, once we've calculated this high resolution phi, we no longer need the low resolution. In our computer codes, I still call this phi, but here it's phi 2 to designate that it's actually on a high resolution grid. From this, we'll calculate the analog grating, then the binary grating, and then we incorporate fill fractions. So this fill fraction will be an input map, just like theta and period, but since it's implemented on the high resolution grid, we actually define it that way from the beginning. The important thing is that this coarse grid, or low resolution grid, and the high resolution grid, they're talking about the same physical amount of space. It's just that the high resolution grid uses more points to do it with. Okay, so once we have the grading phase, and that was on the low resolution grid, we interpolated it up to a high resolution. So now we're looking at a grading phase on a high resolution grid, and it looks no different, and it shouldn't. But now we can calculate the analog grading, also on the high resolution grid. This is just one little line of code, and it's epsilon equals cosine phi. So there's our analog grading. That shouldn't surprise us. We've been calculating it this way all along. So now we have our analog grading. Last step is to calculate our binary grading, and just using a simple threshold technique and the epsilon 1s and the epsilon 2s that we defined at the beginning of our code, we can convert this to a binary grading. And in this case, the white areas are 1s, or I'm sorry, the white areas are values of 2.5, and the black areas are a value of 1. Now typically, if I'm doing these things and I'm going to convert this to a CAD file, I just leave the black and white as 0 and 1. But if I want to instead import this into an electromagnetic simulation, 0s and 1s don't make sense there. I may actually need to convert this to real permittivity values like 1 and 2.5. But now we have our binary grading, and we are essentially done generating a spatially variant planar grating. So if this threshold value is a function of position, we can control our fill fraction as a function of position. One might ask, if we know that we want a fill fraction of 35%, how do we know what the threshold value is to realize that? Well, here's a way we can do that. We build a function of fill fraction. This is more intuitive for us to understand. And the threshold value we need to realize this fill fraction is simply cosine of pi times f. So here's a trend where we're showing this analog planar grating converted to binary form from f equals 0 all the way up to 1.0. And here's the threshold values it would take to do that. And we've calculated these threshold values from the cosine of pi times f. Now, even when our gratings are not perfectly cosine, as long as it's close, this is a pretty good way to approximate the fill fraction. When we get to the MATLAB codes, we will adopt a more rigorous way when we don't have just planar gratings, but we still want to control the fill fraction. But for planar gratings, this works really, really well, and it's not really necessary to do anything else.